Hello everyone, we are starting a free open lecture in our Discord. All our lectures are held weekly without interruptions. If you, the viewer, want to ask questions and receive answers in an online format, join our lectures. You can find the link to Discord in our Telegram channel. To find out the schedule for the lectures, join our Telegram channel. So, accordingly, we have defined how our profile will be stored. Now the most interesting part begins. It is necessary to find all possible profiles and information about how they are connected to each other. That is, we have a profile like this, and then there is another one with its own numbers. To elaborate on the profile, we can provide more details about the numbers, such as their significance and how they are calculated. 1, 2, 3, 3, 2, 1. Here there will be, for example, 4, 5, and 5, 5. And accordingly, we need to understand whether we can obtain a string here during the transition between profiles. This means we need to determine if a string can be captured or generated during the switch from one profile to another. Can we get a string on the stack that has two profiles, one on top and the other below? Profiles, in this context, refer to different states or configurations that a system or application can have.
Want to become a great programmer? Subscribe to our Telegram channel.
That can help you on your journey to becoming a skilled programmer. We will need to iterate through all possible profiles on top and the possible profiles below to determine if they are compatible. This involves checking each combination of profiles to see if they can work together without causing any issues or conflicts. And, accordingly, calculate the number of ways to transition from the top row to the bottom row in a systematic manner and thoroughly by considering all possible paths from the initial position to the final destination. We will pre-iterate in detail which profiles are compatible with each other and thoroughly in a detailed and thorough manner. That is, it seems similar to what was in the previous task. Here we iterate through all possible profiles at the junctions of the strings. From this, we construct a graph. That is, if we have an edge, then it means we can transition. For example, from 1, 2, 2, 1 to 4, 0. But we won't be able to go back. It's impossible to achieve that. For example, from 4, 0, you can reach 1. 1. 2. 2. So, accordingly, we get such a graph made of edges. This graph is constructed by connecting various nodes with edges, representing relationships or connections between them. Once the graph is established, we will then initiate a breadth-first search algorithm. This means we will systematically explore the graph layer by layer, starting from the root node and moving outward, visiting all the neighboring nodes at the present depth level, down from the current string along some profile to the next possible profiles, and then we will keep descending further and further. This is a kind of unique traversal. So, accordingly, how can we understand if it is possible to transition from profile A to profile B? It is necessary to restore, accordingly, the string between the profiles. Since the information about transitioning to the previous string, the next one, and the cell to the left in the string is available, it is possible to unambiguously restore the string or understand that it cannot be obtained. The restoration of the string occurs step by step. That is, we move from left to right and gradually restore it gradually. In order to determine the path numbers in addition to the string, it is essentially necessary to number the paths of the next potential profile in advance. Profile A remains as it was, meaning we do not touch anything at the top, while profile B will be renumbered further in ascending order. So we have 1 and 2 occupied here, and we will number 3, 4, and then 6. Well, by traversing the columns, the string will be restored. When merging paths, they will receive the same numbers. This will allow us to identify cycles and prevent them when it is not yet possible to do so. A cycle is possible only if there is one path left that we have not yet numbered or connected to each other. Otherwise, there should be a transition to the zero state, meaning there should be no transition to another string. This, accordingly, is an example of how to obtain an intermediate string from one profile and the second. After we receive a new profile, which contains all the necessary information about the user, it will need to be renumbered to avoid any potential duplicates in the system. That is, so that we have unique strings that are renumbered in order to ensure that each and every string is uniquely and properly renumbered. I didn't duplicate anything during the transition. So essentially, accordingly, this is briefly what our solution will be about in next. Initially, all possible profiles and the connections between them are searched for. Then breadth first search is initiated, where all possible variations are found in the profile reachable from the current vertex. To understand almost at whether it is before this vertex or not, a bit mask is assigned to the profile. In the mask, the path number will be encoded, which is why there is a restriction of m not exceeding 7, because we will have 2 bits allocated here, and 2 bits can accommodate a maximum digit of 3, so we can have a maximum of 3 unique paths. During the breadth first traversal, an adjacency matrix is constructed, where if we have a 1, it means we can move from one state to another, such as from profile P1 to profile P2. Next, we will have the main DP, where the task will be to sum the number of traversals of the first I rows, where the transition from the ith row to the I plus 1 is defined by profile P, and the recurrence formula, which is a mathematical expression used to define a sequence recursively. What we counted in the previous lines, referring to the earlier steps or stages in our calculation, and compatible profiles, meaning profiles that fit or match the criteria, is passed to the current profile. The initial value for position 0.1, which is the starting point in our sequence, will be equal to 0. This means that for the 0 row, the profile defined by a simple one, which is a basic or elementary profile, will be equal to 1. So, why a 1? It should be 0, 0, because if it's 0, 0, then our profile will be defined purely by zeros. This precisely means that from the first row, it goes flat like this and then goes down. Something interesting and captivating. Or not, by the way. It depends on your perspective. By the way, we might have some other transitions here, which could be quite intriguing. Do you have both, or can there be? There can be. Let's take a look at what starts and emissions are available on the path. Is the TFSP with emission 0 generally set everywhere? We definitely need to take a look at the slogger right now. Got it. Absolutely. Well, okay, strange. As if there could be something else to use for the starting value. But this is the code for verification, so most likely it counts everything as it should, right? Before returning to the code, let's actually discuss the very idea of what is happening here. Are there any questions or concerns that you would like to address? If you have any doubts or need further clarification, please feel free to ask now. We want to ensure that everyone understands the material. That is, we essentially have the idea of what is happening. We basically create a graph from possible transitions between lines. We look at when they are compatible with each other. From this, we essentially build a complete graph. Next, we thoroughly go through the lines and iterate over the profiles, respectively. From the profiles, we iterate through the possible transitions further, the edges. And so we simply add up the number of ways to transition to the next line, to the next mask. Does anyone have any questions or need further clarification about this particular idea that we have just discussed? Yes. Let's do it. How do we check if the profile is compatible? How do we restore the line? And what about this? It will be now. It will be right now. Moving on. These are already questions of implementation, actually. So, what do we have here? We have an array with the profile of where we are coming from and where we are going. This array provides a detailed representation of our starting point and our destination. There is a profile of the lower line, indicating our destination, meaning the lower profile should be an auxiliary array that we will use to repaint profile B. This auxiliary array is crucial for accurately repainting the profile. With the help of this queue, we will build our graph. The queue will assist us in systematically constructing the graph. Accordingly, the graph itself is an adjacency matrix, calculated by a function, meaning we will store dp in 2 rows, with one being the previous row and the other being the next row. Well, yes, something like those auxiliary intermediate ones indeed, perhaps, or so. This is the number of vertices we have passed, to the best of my knowledge and recollection, up to this point in our journey, as far as I remember. This thing, by the way, I don't remember what it is. This might be a visit, meaning whether we have already checked this line or not. Let's see. This step, we proceed by adding the specific number that corresponds to the game we previously assigned. This is crucial for tracking purposes. Now, the question arises, do we have this particular visit recorded here in our system? It's important to verify this to ensure accuracy in our record. No. So it turns out without him, okay? So, what's happening here? Essentially, we are iterating through the mask from which we come. We take a mask from the queue, where we arrive at the designated location, and then we carefully check if they are compatible with each other in terms of size, shape, and material. That is, to begin with, we initially convert what was stored in the queue into a standard or normal form, which is a process where we transform the data into a more usable state. Next, we record the bit representation of the transition mask in the array B for the current mask temp, ensuring accuracy. That is, we also simply convert it to a normal form. Next, we basically check if the strings can essentially be concatenated. If possible, there is only one way to check this, and it is done through the join function. We won't open it for now. We also need to figure out the constructor, which is a crucial part of our process. Next, we have the transformation of the profile into a mask, which is another important step. That is, we essentially transform the axis in B into a mask. Therefore, it becomes more defined and clear. So for this mask, we create a vertex and then carefully add it to the total count in order to ensure accuracy. We also add this vertex to the queue because we will later iterate through all of the various possible masks for it. Subsequently, and accordingly, we add an edge to the adjacency matrix. That is, this is where we came from and where we came from. So, it turns out that in the queue, we store where we come from, while in the battle and the mask, we iterate over where we are going. From this, we determine our path based on what happens in the constructor. If there are any questions, we will analyze the transition function slowly and carefully. TFSP, what is happening here, how we essentially assemble the graph, is not very clear, specifically and precisely. In detail, in the queue, we store where we come from, while in the battle and the mask, we iterate over where we are going. From this, we determine our path based on what happens in the constructor. If there are any questions, we will analyze the transition function slowly and carefully. TFSP, what is happening here, how we essentially assemble the graph, is not very clear, specifically and precisely. Are you asking about everything in general, or are you referring to something specific and separate? No, I am talking about everything in its entirety, without exception, all right? Let's try to write this down in a way that is more abstract and understandable. We have a queue. In the queue, we store vertices, for which we will iterate over the next vertices. And accordingly, you check thoroughly whether they can join together or not, in order to ensure they fit and completely work together. The queue is located in the array. Using tail, we move from one vertex in the queue to another. That's how it works. Next, we have essentially entered the current element in the queue. We are basically iterating over the mask of the next row for it, essentially. Let's transform both of them into a normal form. That is this one and that one. Here we transform the battle mask that we are currently iterating over in this process. Here we take the current vertex from the queue and then also transform it into a human readable form. And at this stage, is it clear what is happening? Here's what we are doing. The essence of this file. Do we currently already have profiles that are stored in the queue right now, at this moment? In the queue, there is a starting profile that is initialized with zeros, and we will be adding new ones from there. So we have a starting point from which we begin iterating through everything, and then we proceed to add new elements. This is a sort of unique count of the vertices that have already been traversed, which is essentially the addition of the next element to the queue. Next, after we have created normal strings that can be compared with each other, we use the join function to check if they can be joined or not. The join function is crucial here, as it determines the compatibility of the strings. If the strings are compatible, the transformation is successful, and we achieve the desired battle mask. If so, we transform the profile into a battle mask in this way, meaning we had some array B. This process ensures that the strings are properly aligned and can function together as intended.
By the way, we transformed it into the desired form in a way in the join function, like this beautiful one, and then we translate everything into the battle mask, which is quite fascinating. Next, we add the vertex to the queue and create an edge between the two vertices, which is a crucial step. Here, there are some questions about how we create the vertex and why we create the edge here. For now, this is still magic happening, and it is quite intriguing. Additionally, this process involves several intricate steps that are essential for the final outcome. Are we adding a vertex to the queue in the process of our algorithm, and then subsequently looking at that vertex again later to ensure completeness? Yes, that is to say, before this vertex was, we are considering two profiles, right? A and B. From A, we go to B. To start with, let's direct our attention to our primary vertex, which we will refer to as vertex U. This vertex is crucial for understanding the structure of our graph. At first it was equal to B, meaning that they entered it and tried to shape it, where A is on top and B is on the bottom. Then, after we carefully and precisely created this edge in a detailed manner during the process, we entered this vertex. U step by step, and now it will be some A that will try to connect to other vertices, meaning that essentially, while iterating through the elements in the queue, we attempt to create directed edges from each of these vertices to the next vertices. This is how we do it. To provide more context and details, this process is crucial in graph theory and computer science. By iterating through the queue, we ensure that all vertices are connected in a directed manner, which is essential for various algorithms. For example, in a breadth-first search, this method helps in traversing the graph efficiently. We have a vertex ahead of us, in front of us, and we are trying to move from it to other vertices. This is precisely how the graph will be constructed. And there we check. If we can successfully create an edge between these vertices, yes, in order to
Want to become a great programmer? Subscribe to our Telegram channel.